Okay, so let me explain one more time. So thank you for Sinyo. You give a good critic on my slide. So when we are doing with the digraph, the directed graph, if you still remember, we are going to find the Aij and we will compare the Aij with the Aik plus Akj. So what is this one? Let's suppose I have this matrix for the first time. 0, 3, and then why this is infinite? 1 to 3 is infinite because there is no direct edge from 1 to 3. So the original distance, or we say this is A0, is infinite. And 2 to 3 is also infinite. 2 to 3 is infinite because there is no direct edge from 2 to 3. So if we want to find this one, then we will use the Floyd-Warshall algorithm to find the shortest path. The same with the other infinite, 3, 1, 3, 4. So there is no direct edge, so it is infinite. We will do for every step to update the infinite. We will do the iteration 1. When we do the iteration 1 means we are making the k equals to 1. When k equals to 1, so we close this one and we close this one. Because k equals to 1, so we close the row 1 and the column 1. And we try to find other section, other cells, and we are going to update it. So how to update it? As I mentioned to you before, we will check if it is infinite with 2 plus infinite. So we need to find what will be the minimum one. So if it is infinite, and then it is also infinite. Okay, so this is, I made some mistake before. So I updated with this one is the infinite. Because 2, 3, 2 to 3. If we go to 2, 1, and 1, 3, it is still not possible. Because 1, 3 is still infinite. So we still keep just infinite. Even though later we can find with this one, okay? But at this moment, there is no direct, or there is still no information about 1, 3, because we have not reached k equals to 4. So k equals to 4 is not available. So we keep this one as the infinite. And also the other part, okay, so you can check. So A to 4, what is A to 4? A to 4, we have 4. If we go to 1, A to 1 is 2, and then A14 is 5. So 7 and 4. So the minimum will be 4. 2 and 4. So we put the minimum, which is 4. And let's say 3 to 2. 3 to 2, we put 1. Compare with 3, 1, 1, 2. 3, 1, it is infinite. And 1, 2. 1, 2 is 3. So we will use the minimum, which is 1. And what about 3 and 4? 3 and 4, it is infinite. We have 3, 1 plus 1, 4. 3, 1 is infinite, 1, 4 is 5. So infinite and infinite, we just keep the infinite. What about 4, 2? 4, 2, we have also no direct edge here. So for 2 is infinite. And then we have for 1 and 1, 2. For 1 is infinite and 1, 2 is 3. So this is also infinite. We just keep this as infinite. For 3. For 3 we have direct edge for 3. So it is 2. Compare with the for 1. For 1 it is infinite, and then 1, 3 it is infinite. Then we use the minimum, which is 2 for this short span. Okay. After we have this matrix, so we are going to use this one for the next one. Okay. So we already update the matrix here. This is the iteration 1 result. And we will use this one to update our next matrix, which is we call as the A2. The A2 means the K equals to 2. So we again do the same thing, and we will check what is the minimum. And then after we have this matrix, again we will check, and we will use that iteration. We will use this result from the iteration 2 to update the iteration 3. With this information, we can update what is the result, and then again we will update until the last one, which is K equals to 4. So last time I didn't put the K equals to 4. Now I update it with the K equals to 4. This is the result from the iteration 3, and then it is used to update the A4. Okay. So please take a look on this calculation. So I checked several times. I hope there is no mistake with this equation. Okay. And if you have any question with this one, please let me know. So that's the way of the Floyd-Warshall algorithm. We will do for every iteration. And as you might know, the K will go from 1 until 4, the I will go from 1 until 4, and the J will go from 1 until 4. That's why the big O notation of the Floyd-Warshall is On power of 3. That will be the worst case scenario, because there will be 3 kind of loop. The loop for K, the loop for I, and the loop for J. Okay, so that's my update about the diagram. Let me continue with the binary search tree. So in the binary search tree, we already learned about the binary search. This is the binary search that we learned previously. But how if we combine? We combine not using only the binary search, but we are going to use the tree for finding a target. In this case, if we want to find a value 7, so we make it half, and then make it another half, and then make it another half, and okay, we can find the numbers that we are searching on. This is the way to do the binary search. Okay. So I would like to teach you if we want to use tree. So the tree, we learned there are 2 kinds of tree. Okay. The first tree is the rooted tree. Okay. The rooted tree means you learn about the tree before the graph. We have root, or that is the ancestor. Okay. We have like sometimes we call it parent, okay, we call it grandparent, and etc. That's the first type of tree. And the other kind of tree is from graph. When we learn the graph, we also learn about the spanning tree. We learn about forests. So those kind of tree, yeah, it is related with graph. There is no root because every node can be the source and every node can be the destination. That's what we call as the graph. Let me get back to the rooted tree for this problem. So this problem is still using the rooted tree. So I will try to combine some of the data structure and some of the algorithm that we already learned. So in this case, we are going to use binary tree. You still remember binary tree? The binary tree means we have at most 2 children, left and right. Okay. And I hope you still remember we have the proper binary tree. In the proper binary tree, we have exactly 2, left and right. Okay, we have exactly 2, left and right. This binary tree will store the key. If you are doing with the dictionary, we know that the dictionary contains key and value. And we are going to use the key only because we are going to store the key in the rooted tree. So the nodes will be the key and it should satisfy the following property. So let U, P, and W be 3 nodes such that U is in the left of subtree V. So U is in the left of the subtree V and W is in the right subtree of V. So W is in the right. And then we have key U, so this one is less than or equal to key V, and then the key W will be greater than or equal to key V, key W. So this is the property. If you take a look, let's say if I have 6 as the root key, then the left will be smaller or equal to the root. And in the right part, it should be greater, okay? Greater than or equal. This one should be smaller. Oh, okay, that's wrong. Okay, 2 is smaller than 6. And here 9, it is greater than 9. So 9 is greater than 6. That's the property. External nodes do not store items. Instead, we consider them as node. This is external node. There will be no value here. There will be no such value. We call it node, or this is the external nodes. In an in-order traversal of a binary search tree, it visits the key in increasing order. So if you still remember, we have pre-order traversal. We have post-order traversal. Okay, we have pre-order traversal. We have post-order traversal. Those two are used as the traverse for the common tree. If you have binary tree, then there is one unique traversal. We call it in-order traversal. And in order traversal, we use the search from the left, and then we go to the left. We go to the right. If we want to search, if we use the binary search, we just split into two, and then we search again to the next, whether it is to the left or to the right. So the idea is the same. When we are doing with this tree, binary search tree, if we want to search the K, we trace a downward path starting from the root. The next node visited depends on the comparison of K with the key of the current node. If we reach a leaf, then the key is not found. Do you know leaf? Leaf is the external node. Okay? So this is the leaf. This is the leaf. So if you already reached leaf, and if you still cannot find any numbers, then it means you do not find the key. So let's say I have a problem, find 4. So we can use the call tree search for comma root. So this is the algorithm. T is the tree, okay? And then P, we have the P is the collection of key, and then K is the number that you want to search. Okay. So I'm going to find 4. So if K equals P dot key, and if 4 equals to this node key, then just return P, just return this node. But if it is not, then we will check K is less than P key. So if we have this one, 4 equals to 6, no, then we check this one. 4 is less than 6, 4 is less than 6, and T left, the left side of this tree is not known. It's not known means it is not a leaf. Then okay. Then you will go to the tree search. Again, we will use the tree, and then the next will be the T left P. So we will use this T left P, and then we still use K, what the number we are going to find. So we will have 4 as the K. It is still the same. Now we will check. This is the recursion. Now we have the T and T left P, which is 2. So again, we will check this one. K is 4 equal to no. Then we will go this one. k is less than p key. So 4 is less than 2. No. Then we go to this one. K is greater than P dot key. So 4 is greater than 2. Yes. And then check the right P. The right P is not known. Okay. There is a value here for. Then we will do this one. 3 search T. And then we use this right node, which is 4. And then K will be the same. K is still 4. So we will do again the recursion. And now we will check this one. The position is here. So 4 equal to the P dot key, which is 4. Yes, it is true. Then we will return the P. The P is the node. Then return P. The algorithms for nearest neighbor queries are similar. So in the nearest neighbor, usually we try to find the nearest one from the searching point. As you might know, in any algorithms or in any ADT, we will perform like insertion or deletion. Now, if we are going to add one value, let's say I'm going to put k comma o. So k is a key and then o is the object. And we are going to use the tree search. Assume that k is not already in the tree. So if I want to add k, but k is not in the tree. Okay. And let w be the known leaf reached by the search. So let w is known. We want to insert k at node w and expand w into an internal node. So I'm going to use this w. I'm going to use this w as the new node. So the w will be changed to internal node. Let's say if I insert 5. What is inserting 5? The same with the 3 search. I have k equals to 5. 5 equal 6? No. So 5 is less than 6. We go to this one. Again, we check 5 equal to? No. So 5 is less than 2? No. 5 is greater than 2? Yes. So we go to the right. Again, we check 5 equal 4? No. 5 is less than 4? No. 5 is greater than 4? Yes. So we go to this section. Because it is known, we are going to replace this one. We use the function put k comma 0 to update this one. So we update the w into a node, create a node 5, and then we create a new node. This node will be the leaf. Okay. So this is the pseudocode. We call it the tree insert. So the 3 insert means if I have a P which is a 3 search, we are going to search. We want to find where is the possible P, where is the possible node to insert a key. So if we can find a P, then yeah, you can just use that to set a new value. But if you are not able to find a node with the same key, then you are going to add the node. If the k is less than the p key, then you put into the left. If it is greater, then you put into the right. What about if we want to delete? So the deletion, there are 2 kinds of deletion. So this deletion is to remove. We are going to remove a k. Let's say I want to remove 4. So we will first search where is the k equals to 4. So we can assume k is in the tree. So this is assumption. So we assume that k is available. And then let v be the node storing k. So let's just use v. This is the node that stores the k. If v has a node, known means this gray color. If v has a non-leaf child w, we can remove v and w from the tree with operation remove external. With remove w and its parent. Okay. So for example, if I want to remove 4, so first I will do again with the search 4 equal to 6. No. So 4 is less than 6. We go to the left. 4 and then again check with 2 equals to 2. No. 4 is greater than 2. So we go to the right. Okay, now we find 4. What we are going to do here is you can delete 4. But once we remove 4, there is a remaining node here. In this case, we are going to remove this set. We are going to remove v and we are going to remove w. So after we remove those, we will have the new node like this one. So the node 5 will be the next after 2, and then there will be 2 nodes just as the node 5 before. So we will remove the v and w because it contains the node. Now there will be another case. How if we want to remove the node and node v have children that both of them are in the node. So in this case, I want to remove 3. In this case, 3. If I want to remove 3, we have 2, which is a children internal node, and then I have 8, which is another children, and this is also internal node. Then how can we remove this one? There is a way, there's a step to do this one. First, we find the internal node w that follows V in an order traversal. If you still remember the in order traversal, we will find the key in the order. So after I have 1, I will go to 2, and then 3, and then what is the next? There is no 4. So the next is 5. Okay. And we find the internal node W that follows V. So we find 5. Okay. After we find the 5, and then we copy the key W, and we are going to update in the location of V. Afterward, we remove the node W. So we remove node W. And of course, you will check whether there is a known, there is a leaf or not. So we can see there is a leaf, and the leaf is in the left. So we remove the external, and after we remove the external, it will be updated. So the known will move as the known of the next possible from the in order traversal. So you can see here, this is the updated one. I want to delete 3. Okay, I want to remove 3. So we will start from the root. 1 equal to 3. No, yeah, we know that 3 is higher than 1. So we go to the right. Okay, we find 3. After we find the 3, we want to remove it, but we have 2 and we have 8. Instead of inserting 8 into V, we will check the next node, which is 5. And then after we find 5, we will update the V with the 5. And then we will remove this one, and this one will go up, and this will be the updated 3 after the deletion. The performance. If we consider an order map with n items, implemented by means of binary search tree of head 8s. So we have these 8s. This is the head. So the space is on, and then search and update methods, it takes O8 time. So it depends on the number of the head. So if you search and update, it will take O8. The head 8 is on in the worst case. The worst case, it means if we have 1, 2, 3, 4, 5, then it means h equal to n. Okay. So in the worst case, we have h equal to n. That's why on is the worst case. But in the best case, we will have O log n. Yeah, in this case, it is O log n. So the head is almost half than the number of nodes. 1, 2, 3, 4, 5, 6, 7. Okay. So log 7. So it is, if it is base 2, okay, probably is about 2 something, maybe 2.8, maybe approximately it is 3. then yeah, it's almost like half. Okay, I think I will shortly explain this one on Friday.